In this second lesson of the Unit 3 multiple stream, we're gonna see how to combine energy needs and how to build and match composite curves. This minimum heating utility we are looking for are the thermal flows that will be sufficient to meet the combined needs of all cold streams. And the similar thing for the cooling utility that will meet the combined needs of all hot streams. Then we must combine the energy needs of hot stream and cold stream, and this combination must take into account both temperature and enthalpy flows. For doing that, we're gonna use composite curves in the temperature versus enthalpy diagram. In a composite curve, the needs of enthalpy flows of different streams are combined along temperature interval. A combination for this interval, a different combination for this second, third interval. Then, for the first interval, the lowest one, there are just this stream with this duty. Then, for the whole system, the combined needs are exactly this duty along this change in temperature. For the second interval in temperature, we got two contribution of two different streams, and the combined needs of the whole process are the summation of both contributions along this temperature. And so on. Then, composite curve summarizes the heat flow requirement of a stream in terms of temperature. Then, the explicit procedure to build the composite curve, in this case the cold, is take every cold stream in the problem. Divide the problem into temperature intervals, placing boundaries where one cold stream at least starts or ends. This is because we don't want streams ending or starting in the middle of an interval. Then assign the enthalpy flow as 0 at the lowest boundary. And for each other boundary, we calculate the contribution of every stream with its particular MCP along a change in temperature, an interval, and sum up with the previous enthalpy flow across the boundary. We obtain then a pair of temperature and enthalpy flow along the different boundaries that form the coordinates of the elbows of the composite curve. Then for this hot composite, you see here the 0 heat flow at the first boundary, 40 Celsius. For the second boundary, 80 Celsius, something like 1600. For the third interval, the enthalpy flow will be something around 4700, and the upper interval for 180 Celsius and more or less 5500 kilowatts. In composite curve, you can identify in the individual streams running from elbow to elbow. In this composite curve, hot, you can identify stream number 1, that individual is something like that. Stream number 2, that individual is something like that. When they are alone, they coincide with the complete composite curve, and at the interval where they coexist are combined to form this part of the curve. At this point, you should realize that regardless of the complexity or number of streams, every process gets just one hot composite and just one cold composite. It doesn't matter if you got 2 hot streams or 71 hot streams, you got just one hot composite curve and one cold composite curve. And this fact allows us to analyze the problem as if there were only 2 streams that we have seen already. Then we can treat this composite curve at the simplest straight line streams and match them at the concrete minimum approach and look for the hot utility we need or the cold utility we need. This will be the way we analyze multiple stream processes. To finish the lesson, you must know that sometimes we include in the same composite curve utilities and process stream. Here we are combining the process stream 1 and 2 with the heating utility here. This is a combined composite curve. And in the cold combined composite, you can get the cooling inside. 4 plus cooling here, 3 plus 4, and 4 stream here. And if the duty, the enthalpy extension of both composite curves are the same, they are said to be balanced. Balanced combined composite curve. For example,